Okay, I think we are live now. That's
Okay,
awesome.
we're live.
Yes, we are live. So we have, so my name, I'm Ashwini, and we have Shankadip. Shankadip, you can tell me what you're doing.
Excuse me?
Yeah, can you tell me a little bit about your background so that people understand?
So, I'm from Kolkata, Khordha, and in school, I was very interested in mathematical Olympiads. Then I tried RMO, I went till INMO, and after that, I did my undergraduate at CMI. And after that, I came to Brazil, INPA, and I'm doing a doctorate in dynamical systems.
So those who do not know this, yeah, IMPA is one of the best places to do work in dynamical systems, which is awesome. Shankadip is also a trainer at Cheenta. So he is one of the key trainers, in fact. So today we are going to discuss a beautiful problem that he was talking about. You can tell us about the problem, Shankadip? Then I can sort of word.
So,
Yes, yeah.
the problem says that suppose we have an n-gon which is not regular.
Okay.
Okay, it's regular. Not regular means the sides are not equal. All so you know what a regular n-gon is. It's not regular. It's not concave, which means it's convex. So no angle is greater than pi. So every angle is less than pi.
I see.
And has a point O inside. So let us draw the point first. Suppose we have a hexagon.
Right.
So it has a point O inside such that if you form the n triangles like this,
Mm-hmm.
the areas of these triangles are equal.
Okay, I see.
Okay.
So this will not happen for all points, right? It will happen for
No, it has one point.
I see. I see.
So we are looking for triangles which satisfy, sorry, not triangles, polygons that satisfy these three properties: non-regular, convex,
Okay,
and has a point O inside such these areas are equal.
I see. I see.
So the existence of such a point for a
Uh-huh.
triangle is obvious. Any triangle, in fact, you can get such a point for any triangle which is the centroid.
The centroid, yes. Okay.
Yes. So the centroid satisfies this. These three triangles have the same area.
So, I mean, let me understand this. So, if I put a dot at the centroid of the triangle, and
Yes.
if I measure the area of the three triangles, all the three areas would be equal. Is that what you're saying?
Yes. Yes. All the
And
three areas
is there
are.
an easy way to say why that is true? Like,
Why that is true?
yes.
Okay. So it's because see, these two sides are equal.
Correct, because it's a centroid, so it's a median, of
Yes.
course.
So these two lengths are equal.
Right,
So
right.
let me use a different color.
Sure.
So these two triangles have equal area.
Aha. Right. Correct.
Then, from the same logic, these two triangles
Okay.
also have equal.
The smaller ones also have equal area. Okay.
Yes, that's why the this one here and this one here have the same area.
Okay. That's
Okay, so for a triangle, you always have such a point. But for higher for polygons with larger number of sides, it's not clear.
uh
Okay,
right. Right.
and note that if we relax one of the conditions, if we allow the polygon to be regular, then it always
Uh-huh.
holds because uh, every regular polygon has a center, and that center is symmetric with respect to the sides. So this
Correct.
property holds. Okay.
Uh-huh. Right.
So a regular polygon can be a good starting point.
Right. So it always works for regular polygons. You just take
It
the center.
always works for regular polygon.
Uh-huh.
Okay. Now, Uh, the reason I wanted to discuss this problem is because this
Mhm.
is a departure from the regular way of thinking. Okay,
Okay.
usually we draw a diagram and we try to construct something, we try to see angles, etc. In
Yeah,
this problem, it is very advantageous to think in terms of transformations.
I see. Okay.
Why? Because a regular polygon clearly satisfies, um clearly has these properties, and a polygon which is very close to that regular polygon
Mhm.
and but is not regular should also have that property.
I see.
Okay. In other words, if we take a map f from R2 to R2
Okay.
such that f of the regular polygon
Uh-huh.
is
Oh, I see.
a nearby polygon.
Okay. Okay. So when you say transformation, you are talking about this map from our.
Yes, I was talking about this map.
I see. I see. Okay.
Then uh, we can try to find such a transformation such that it makes a regular polygon non-regular while
Okay.
preserving the other two properties.
So the areas are still same. So the
Areas
transformation
are still
does not.
same, convexity is preserved,
I see.
but the polygon becomes non-regular.
Wow. That's fantastic.
So now here's a question: why think of this problem in this way?
Uh-huh.
So usually we're taught to just do constructions and stuff.
Yeah.
Why think about transformations?
Right.
And this is a very simple question with a surprisingly interesting answer.
Okay.
So this kind of like deforming geometrical objects
Uh-huh.
is nothing new actually. I think this idea originated with Newton. So
Okay.
in his mind, when he invented calculus, he used to imagine not just Newton. Archimedes also used to do this.
Okay.
So he imagined triangles being deformed and curves being deformed.
I see.
Okay,
I see.
and in modern mathematics, everything is thought of in terms of some objects
Uh-huh.
and maps between the objects.
I see.
Okay, so we often say that other subjects change, physics changes, chemistry changes. So Newton's physics had to change when Einstein came along, right?
Right.
But
Right. Right.
mathematics does not change. Mathematical facts are always true. But
Mathematics.
mathematics does change
Mhm.
in the sense that the point of view changes. We look at the
Right.
same objects in different ways.
Right. Right. Right.
Okay, so the point of view of modern mathematics is whenever you get an object, you
Mhm.
try to look at transformations.
Acha.
This is the general philosophy.
Okay.
So whenever you get a problem, it's always most of the time it's useful to think of transformations of that object.
Right. Correct.
Okay.
So one of the things I mean, let me since you are talking about this, uh,
Yeah.
it's a very interesting point that you made that the viewpoint changes. I was teaching angles to kids the other day. Okay. So for ancient Greeks, angles were just shapes, just like triangles or squares or stuff like that. Because angles are even in like as early as Holland Stevens geometry, you would see that angles are basically the structure created when you to raise meat at a point.
Yes.
But it is also so that angles measure a transformation, that is rotation. So,
Yes.
in a sense, a shape is now given a task to measure the quantity of a transformation.
Yes.
That is, I kind of find it fascinating that the arc over radius thing,
Yes.
the
Yes. It's
fundamental,
quite ingenious.
it is quite ingenious that you would measure rotation in that way because, of course, angle was obtuse, angle was acute, angle was right because clearly they were talking about shapes, but now they're talking about these measurements and something is going on. So yes, the point of view changes, as you said. So we must study transformations. And as you mentioned, you can go on now. I just
Okay,
thought I would make this point.
let's go on.
Yeah.
Uh, and I will get a new board.
So there is a transformation that takes a transformation is a function from R2 to R2.
Yes,
That
R2, R2.
transformation is taking this regular polygon and mapping it into this convex irregular polygon
Yes,
in
with
the,
the same property.
with the same properties, that the areas of all of the pieces are preserved.
Yes.
Okay, I see.
And what are the properties that we require from this map?
Uh-huh.
First, it should map lines to lines
Right. Okay.
because otherwise give a line and you get a curve and it's not a polygon anymore. It's something else.
Sure.
Okay, so first requirement is maps line to lines.
The maps line to lines. Okay.
Lines to lines. The second requirement is it either preserves area.
Right. Or maybe it scales
Yeah.
area by the same amount.
Yeah, so it either preserves area like an isometry
I see.
or it scales area like a dilation.
Ah. So if all areas increase two times, then the
Yeah,
same
so
property
if
is
all the areas of the I mean if the areas of all the triangles are increased by two times
uh-huh.
by a factor of two,
Right.
then equality remains, right?
Correct.
Remains valid.
Right.
So it either preserves area or it scales area.
Correct. Okay.
Second point. Third, it preserves convexity.
Okay. So all the angles are still less than pi.
Yes.
Awesome. Okay.
So we need a transformation satisfying these three requirements.
Okay.
So just from the first requirement,
Uh-huh.
just from one, it
Yeah.
is natural to think of something called affine transformation.
Right.
So what is an affine transformation? It
Uh-huh.
is something of the form f of x y
Uh-huh.
equal to ax plus by plus say x naught comma cx plus dy
Okay.
plus y naught.
Uh-huh.
In matrix notation, this can also be written as a b c d x y plus x naught y naught.
I see.
And why do I write it in this form? Because this is a generalization of the function, say gx equal to ax plus b.
I see.
So
So
it's a generalization of a linear function on
I
R
see.
part.
I see.
Of course, I have to write the domain and the codomain.
Correct.
So it's a generalization of this.
Ah. So this
Yeah.
matrix here, A, B, C, D, is acting as your capital A.
Yes, it is acting as capital A.
I see. I see. And the X naught, Y naught is acting as your capital
B.
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 Okay.
So when you add uh, some vector like this, you get a translation.
Yes.
Okay,
Okay.
so such a transformation, which we call affine, is the composition of a translation with some matrix.
Uh-huh.
And note that the basic transformations that we know, like rotation, translation, reflection, are all affine transformations.
Uh-huh.
For example, if you take A, B, C, D to be the identity matrix,
Uh-huh.
you get x plus x naught, y plus y naught, which is a translation.
Right.
If you take, uh,
Maybe X naught, Y naught you take as 0, 0 comma 0.
yeah, so if you take x naught, y naught as 0
Uh-huh.
and A, B, C, D to be 1, 0, 0, minus 1,
Uh-huh.
you get reflection about the x axis.
Correct. Okay.
Okay? And for rotation, you need to take, I think, okay, I always forget this.
Cos
I'm
theta
sorry.
minus sin theta cos theta, something like that is there. Yes.
Yeah, yeah.
The rotation
So
method.
this is either rotation by theta or minus theta.
Right, right, right,
This is something that I always
right. I
forget.
always get confused with this one.
Yes. So this is either rotation by theta or minus theta.
Right.
Anyway,
Or
so
change your orientation. Change your orientation.
yes, change in orientation.
Okay.
So
So just to back up a little bit, this ABCD matrix multiplication is essentially rotation. This is something
uh,
you're
no,
like,
not just rotation, it's rotation and dilation.
it's so you can take out a constant, maybe divide by, maybe make sure that the determinant is one. So something is going on there.
Yes.
Something needs to be said when a matrix is multiplied to a column vector. But let's suppose we all know it's a rotation times some amount of scaling. Okay.
Yeah, so actually, we are not going to study affine transformations in detail
Correct.
because we will take a very particular transformation which is simple to analyze.
I see. Okay. Okay. Got
Okay.
it. Okay. Fine.
Just to simplify our lives.
Sure. Sure. Sure.
Okay. So,
So those who are joining now, I see 5 viewers now. So those who are joining now, let me just recap that we are doing a fantastic problem from a Brazilian Math Olympiad. And with us, we have Shankodip. Shankodip is also a trainer from Cheenta. He is saying that he has an irregular polygon and he will map it into a regular polygon. And then some properties regarding area will be preserved and convexity will be preserved. And he will show us how. So yeah, please go on. Sorry, I saw 5 viewers, so I thought I should maybe
okay.
align.
Fine.
Yeah,
Welcome, by the way.
yeah,
So, what was I saying?
yeah.
So,
You were saying about this affine transformation.
yeah, so we don't need to get into a lot of details because we'll take a very specific affine transformation, which is easy to analyze. But
Okay,
it is have the idea in mind that this is a generalization of this
okay, I see.
in one dimension. This is
Correct.
a generalization of this,
Uh-huh.
and you can check easily that it makes lines. It maps lines to lines.
Okay, so it maps lines to lines. It also preserves areas. Does it preserve area or scales area? Maybe scales.
We'll get to that in a
Okay,
moment.
okay, got it.
So this first box is checked. In fact, this first condition made me guess this affine transformation because that's the most trivial class of transformations which preserves which maps lines to lines.
Correct. Right.
Okay, so the idea of affine transformations came from the first condition. Okay,
I see. I
now
see.
the second.
Uh,
For the second one, for those of you who know linear algebra, you should recall that an affine transformation or just a linear transformation of the form, say, hx equal to uh, mx, where
mhm.
M is a matrix,
Right.
the area gets scaled by a factor determinant of m.
Acha.
Okay,
Okay.
so you might ask that, hey, is an Olympiad student supposed to know linear algebra?
Right.
No, because you can simply guess the map fx comma y
Mhm.
equal to ax 1 by a y.
Right.
And why should you guess that this preserves area? Because if you take a rectangle
Mhm.
with sides parallel to the axis,
Mhm.
so the length gets multiplied by so one side gets multiplied by a, the other one by 1 by a. So when you do this, you get 1.
Ah.
So suppose this is L and this is B. So
Mhm.
after you do the transformation, this gets mapped to something like this.
Right.
Uh, A, no, B by A,
So it
and
sort of gets
CM.
skewed. Okay, I see.
Yeah, so it squishes in one direction and extends in one direction,
I see. Okay.
the other direction.
Okay.
So it should be easy to guess that this map here
Uh-huh.
preserves areas.
Right.
At least for triangles, you do not need to prove it for very general objects.
Uh-huh.
Okay. And how do you check that? Suppose we have any triangle T in
Okay.
the plane,
Okay.
okay, and the coordinate axis is here.
Uh-huh.
So this triangle, by T I mean the set of all points
Uh-huh.
here. Okay.
Okay, I see.
So this T can be written as T naught
Mm-hmm.
plus R,
Right.
where R is some vector and T naught is the same triangle translated to the origin.
I see.
Okay.
So you just translate by R in some
I
sense.
translate by R. So
Correct.
this is T naught, and
Uh-huh.
translating by R, I get to T. And if you apply the affine transformation on this,
Uh-huh.
which is okay, for convenience, let's take m equal to a 0 0 1 by a,
Okay.
okay, which is just this written in a more convenient form.
Uh-huh. Okay.
Okay, so uh, then m of t is equal to m of this
I see.
equal to mt naught
Uh-huh.
plus mr.
Uh-huh. Correct.
Now, as origin gets mapped to origin,
Right.
mt naught
Uh-huh.
is also something like this.
Okay.
Is also something like this. So it also has one vertex at the origin,
I see.
and this is just a translation.
Right.
And also, the area of T is equal to area of T naught,
Because you
because
just assume if you
because the
want to do
translation does
all-
not matter.
right, the area doesn't change. Correct.
Area does not change.
Right.
So again, area of MT equal to area of MT naught.
I see.
So if you can prove that area of T naught is preserved, then
Mm.
you prove it for any triangle anywhere in the plane.
Right.
So without loss of generality,
Mhm.
you can assume that the triangle has one vertex at the origin.
I see. So we have now created a transformation that preserves the area and
No,
that
we have not checked that.
okay, okay. We have
We
checked
have not,
we
but we
just
know that it maps lines to lines.
in the origin. Okay, got it.
Yes. So one
Okay.
vertex is at the origin,
Mhm.
and I think the area of this is something like half of x1 y2 minus x2 y1, right?
Okay. Yes, yes.
This is
Something.
a well-known formula.
Yes, yes, yes.
And when you map it to some other triangle,
Uh-huh.
the area of that triangle is half into ax1 into 1 by a y2
Uh-huh.
minus ax2 into 1 by a y1,
Okay.
which is the same.
Okay. Of course.
So this map preserves areas of triangles.
Okay.
Okay, so the second box is also checked.
Right.
Lines to lines, areas to areas. Now the convexity is a somewhat delicate thing to check, because for this I will use some a definition of convexity that you probably do not know, which
Okay.
is, so you know that a convex polygon has a corner which looks like this,
Okay.
right? So the
Right.
polygon is here, and this caves in, and it looks like, so this angle is greater than pi.
Right.
So if you take one point here and another point here, and if you join them by a line segment, that line segment has to cross the sides, that line segment cannot lie entirely inside the polygon. So this part here lies outside.
Uh-huh.
So this prompts us to
Uh-huh.
define a convex set
Right.
S in say R2, S in R2, but it generalizes to Rn. So S in R2 is called convex if X is in S, Y is in S,
Uh-huh.
implies that Tx plus 1 minus T into Y is in S for
Uh-huh.
every T in this interval.
So basically, the line you were basically parameterizing the segment joining the two points,
Yes, I'm parameterizing the segment joining the two.
and then you want the entire segment. If the 2 points are in the space, you also want the entire segment connecting those 2 points to be inside the same polygon.
Yes,
That's what you want. If that doesn't
yes,
happen, it's concave. If that happens,
yes.
it's convex. I see
If
what.
that does not happen, then it's concave.
Ah,
So while we are at it, I would like to connect this definition, which is the most general one I know, to some other definitions of convexity you know. Okay. So for example, convex polygons. So clearly, a convex polygon is a convex set according to this definition, like I
uh-huh.
show here. Okay.
Right.
And another thing which is very interesting. For those of you who have studied the Jensen's inequality, you probably know the definition of a convex function, which
Ah.
is if you take 2 points
Mm-hmm.
and you join the 2 points,
Right.
then this line segment lies above the curve,
Right.
right? When this happens, this is called a convex function, say f.
Right.
Okay.
Right.
So this definition also can be restated according to the general definition as follows. So
Uh-huh.
the set y greater than equal to fx
Uh-huh.
in this context is called the epigraph.
Okay.
So a function is convex if and only if the epigraph, which is I will mark this here,
Uh-huh.
this is a convex set.
I see.
And homework,
Okay.
check. Mathematicians always give homeworks.
Yes, yes. Exercise at each
Exercise left to the student.
step to the students.
So homework, check that these two definitions are equivalent.
I see.
Okay.
Okay.
So now we have convexity,
Uh-huh.
the working definition of convexity, and we'll verify this. Okay.
Okay.
So we need to prove that it maps our given f, so the
Uh-huh.
f we are constructing,
Uh-huh.
maps convex sets to convex sets.
Okay.
So if S is convex,
Uh-huh.
then f of S is convex.
I see. That was one of the preconditions that we needed. We wanted
Yeah,
the
that is one of our requirements.
all
This
right.
is the third requirement here, preserves convexity.
Right.
And yeah, so any element, say Z
Mm-hmm.
in Fs, is of the form, say f of Z naught, where Z naught in is S by definition. Okay,
Uh-huh.
so take any two elements f and x uh, and f and y, f
Uh-huh.
of y in f of S.
Uh-huh.
I need to prove that t fx plus 1 minus t into fy
Mm-hmm.
is also in fs for all t in 0 comma 1.
Right.
How do you do this? We go back to the definition, t equal to mx
Uh-huh.
plus 1 minus t my. What is m? Just to remind you, m is, hey, where did I write it? Yeah. M is this.
I see. A comma 0, 0 comma 1.
A001, which is a nice way of writing this function.
All right.
Okay. And you can easily check that this is the same as mtx plus m of 1 minus ty
Mhm.
equal to m of tx plus 1 minus ty
Okay.
equal to f of tx plus 1 minus ty.
Right. But Tx plus 1 minus Ty was already inside because of the convexity of the earlier thing, right?
Yes.
I see.
So as x and y are in S,
Uh-huh.
this thing is also in S.
Correct.
So that's something we don't need to check anymore.
Ah,
So done. So
that's
if
great.
S is convex, then Fs is also convex. So
Excellent.
all the three boxes are checked,
Great.
and we have a transformation that maps a regular polygon to a polygon we desire. We
Uh-huh.
still have to check that this new polygon, this image of this regular polygon is not regular, but that's very easy.
I see.
So, because it expands at one direction, it expands along the x-axis, and
Uh,
it squishes along the y-axis.
so automatically, yeah.
So yeah, so a regular polygon cannot be mapped to a regular polygon.
This is a good exercise as well that people can try. I mean, think. I mean, imagination exercise.
Imagination exercise, yes.
Okay, that's great. So this is an awesome problem. I mean, this is an INMO level, like national level problem, the national level math Olympiad problem, I believe, from Brazil.
I don't remember. So
Okay.
Brazil has some very interesting competitions. One of them is called Olympiad Revenge,
Olympiad Revenge. Okay.
which is made. This is a Brazilian tradition actually. So all exams, all university exams have revenge exams. So
Ah,
the revenge exams are set by the students for the teachers. Usually they're very difficult, very difficult. So when IMO was held here in 2017, I
oh,
was there.
okay.
I think I was a guide of Indian. Yes, I was a guide of Indian team.
Oh, okay. Okay.
Yes, and we held honoring Brazilian tradition. We held a revenge exam,
Mhm.
and the guy who came first in that exam is our very own Olympiad coordinator, Gugu.
Oh, really?
Who is also happens to be a first class, like world class mathematician.
Ah, was awesome. Awesome.
Yes.
Thank you, Shankati, very much. I mean, I think we are going way beyond the 10 minutes timeline, but this is awesome. I mean, this is a very different way of thinking about geometry problems instead of regular angle chasing and, which using congruences, stuff like that. We now know how to use transformations and think about geometry problems in that way. So thank you very much, and to all our viewers, thank you for watching. We will do these live sessions. So we will try to do this often. Till then, stay safe. Bye.
Bye bye.
Bye.